Okay, so we were discussing magnetic induction field, the B field. And we had already seen the Biot-Savart law, which states that if you have a current carrying wire, then if you take a very small segment of this current carrying wire, then the contribution to the total magnetic induction at a point, let's say R, due to that wire, due to that segment, which is at the position R prime, was given by mu 0 over 4 pi times I times dl cross R minus R prime divided by R minus R prime cube. So this is the law that gives us the magnetic induction at a given point. Of course, we don't always have these current carrying wires. Sometimes the charges just flow through a volume. It can be in empty space, or you might have a large wire, a large current carrying conductor. In that case, dB, you can also write it as mu 0 over 4 pi j at the point R prime cross R minus R prime over R minus R prime cube, dV prime. So this is for an arbitrary current carrying volume. The above is for a line charge. Well, there's a simple glossary to go from one-dimensional charge flow to three-dimensional and two-dimensionals. The idea is if you have a one-dimensional flow, current through a wire, this corresponds in the three-dimensional case to J dV, or we will also be looking at systems where we have these infinite planes which carry a current. So in that case, we will have a surface current density. So this will be K ds. We will also study such systems later on. And we also had certain applications of these. We had one example we had discussed was an infinite current carrying straight wire. And the magnetic induction at this point was, you can also use your right hand, just grab the wire such that your thumb points in the direction of the wire, then your fingers curl in the direction of the magnetic induction. So if the current is moving upward, at this point, the magnetic induction is into the screen. At this point, it is out of the screen. And we had also seen that the magnitude of the magnetic induction was mu 0 over 2 pi, mu 0 I over 2 pi d. So this was where he had somewhat left. Now, any questions up to this point? Anything you want repeated? Yes? Now, J, you see the notation, J is the volume current density. Which means, by the way, as you point out, it is the number of charges passing through an area per unit time. Now, K is the surface charge density, surface current density. It is the amount of current passing through a given length, per unit length of the surface. And then we have I, which is the current, linear current, although this is the linear current, it is the amount of charge passing through a point per unit time. So you see this volume current density, you are right, it is the charge passing through an area, but it is moving perpendicular to the area. So basically it's moving in three-dimensional space.
Sadece magnetüs için kullansak yani geçerli olur mu? Bir şey olmaz. Hani iki vektörü magnetüdünü alıp ayrı iki açılı sinüsüyle şey yapsak.
Well, you should pay attention to one thing. For example, when we were solving this infinite wire example, okay, we considered this point. This is our DL. This is the r minus r prime vector, and dB was equal to mu0 over 4 pi I dl cross r minus r prime over r minus r prime cube. And then dl cross r prime at that point is in which direction? dl cross r minus r prime. This vector cross product with this vector. What is the direction of that vector? Into the screen. You see, it is into the screen whether dl is over here or over here or over here. It doesn't really matter. All the contributions from all the segments are always in the same direction. Now, in this case, when you are summing the vectors, you basically need to sum the amplitudes. So in this example, since all the contributions are always pointing in exactly the same direction, you can only consider the amplitudes. But we also consider this example. Here we have a dl. It creates some dB here, which will be in which direction? You see, at this point, dl is into the screen. This is my dl. This is my r minus r prime. This is the position of my observation point relative to dl. The cross product is in which direction? Well, in this direction. So this is dB. Well, I can consider this other dl. This dl is pointing in that direction. Now, r minus r prime for that dl is pointing in this direction. So what's the direction of dl cross r minus r prime? dl cross r minus r prime is somewhere in this direction. This is dl prime. This is dB prime. These are all perpendicular vectors. So if you add the magnitudes, you will get a wrong answer. They are pointing in different directions. So you have to consider them vectorially. You can, of course, calculate the components of this vector and add the components, but not the magnitudes.
Hocam peki şimdi şu ringi yaptık ya, akım işte ringin üstünden geçiyor. Onu şöyle düşünebilir miyiz zaten? Ortadaki işte şu.
This axis, central axis.
Oradan akım geçsin. Ringin üstündeki manyetik alanı bulmaya çalışıyorum. O zaman formülasyonda bir değişiklik olur mu?
Of course. You see, that is this problem over here. We have a straight wire, current carrying wire. You are calculating magnetic field everywhere else. And this problem and this problem are different. Other questions?
Mesela hocam iç boş küre olsa, onu ben sonsuz ringlere mi böleceğim? Manyetik alanı hesaplamak için. Hem için hem dışındaki manyetik alanı.
You can have, for example, this sphere with a surface charge, and the sphere, you can just put it in rotation. You can rotate the sphere with some angular velocity. And if you want to calculate the magnetic induction at everywhere, that is one strategy. Just divide it into very small rings, calculate the magnetic induction for each one of those rings, and sum them up. Well, this will be the complicated way of calculating it. We will see an easier method. Other questions? Okay, so let's continue from here. You see, this was the magnetic induction for an infinite straight wire. We had this infinite straight wire. Here magnitude of the magnetic induction was mu0 I over 2 pi d. D is this distance over here. It's the distance from the wire. What is 2 pi d? Well, if d is that distance over there, what is 2 pi d? Forget about that b. The circumference of that loop. So if you imagine such a loop, b times the circumference of the loop is equal to mu0 times I. You see, on this loop, b has a constant magnitude. It is always pointing in this direction. This side of the loop is closer to you. This is further away. So I'm imagining this loop. This is my wire. I have such a loop going around the wire. This is just a mathematical loop. If I multiply the magnitude of the magnetic induction on this loop with the circumference of this loop, I get something constant, which is independent of the properties of my loop. But you see, this magnitude times the circumference, I can also write it as b times the integral of dl over a closed path. B is just constant on this loop, so this is the same thing as b times dl, but this is the same as b dot dl, because my loop has this sense, and my magnetic field also has the same sense, has the same direction. So if I calculate the scalar product of b dot dl, then I get just the product of the magnitudes. The angle between them is 0, so cosine 0 is 1, which is equal to mu0 times I. But you see, I can also write I as the integral of some, well, this is, let's keep it this way for the time being. This is my Ampere's law. Now this is, okay, this is valid for an infinite straight line only. That is what we had proven up to now. We will prove it generally, but it will turn out that this law is always correct. Whatever the current is, whatever the mathematical closed loop you consider, the integral of b around any closed loop will always be equal to mu0 times the current running through that loop. Just like the Gauss law. In electrostatics, we have the Gauss law, which states that the integral of the electric field over any closed surface was equal to some constant times the total charge inside. Ampere's law states that the magnetic field, the integral of the magnetic field over around any closed loop will always be equal to some constant times the total current passing through the loop. Well, rather than driving this, we will drive an equivalent relation. You see, b dot dl is equal to mu0 times I enclosed. But you see, the total current is nothing but the integral of the current density. So this is equal to mu0 times j dot dA over some area, over some surface S. But this S should be bounded by this loop over here, because I'm calculating the total current running. If I have such a loop over here, I'm calculating the total current running through this area bounded by my loop. So this S, the surface that I'm integrating over, should have the area, should have the bounding loop, and I'm integrating B around that bounding loop. But now I can do one more thing. If I have an integral over any closed loop, I can write it as an integral over an area bounded by the loop. This is nothing but the curl of B dot dA. over this surface. This should be equal to mu 0 j dot dA over the same surface. Well, this should be true for an arbitrary closed loop and hence an arbitrary surface. But if this is true for an arbitrary closed loop or an arbitrary surface, this tells me that the curl of B should always be equal to mu 0 j. This is what we will be proving. So if we can prove this, this automatically implies that the integral of B dot dl over any closed loop is equal to mu 0 times the total current passing through the loop.
Peki simetri önemli mi?
No, nothing. Well, you see, it will be important if you want to apply this law. Just think of the Gauss law. Gauss law is always true. Well, it's rarely useful. It is useful only if your system is quite symmetric. This will be the same in this law, in the Ampere's law. It is always true, but it will be useful only if your problem has sufficiently high symmetry. You see, to be able to make use of this law in this form at least, you should be able to evaluate that loop integral without knowing what B is. But you should, in order to be able to evaluate that integral, you should have sufficient information about B. Although you might not, you need not know everything about B, you have to have some information about it. Now let's first prove this, and then we will do some applications. Well, we already know what B is if we have any charge distribution. B at the point R is equal to J at the point R prime cross R minus R prime over R minus R prime cube, integrate over all of the volume. dV prime, mu 0 over 4 pi. This is what RB is. Now what is left is take the curl of this and see if it will be equal to the J. So the curl of B. Okay, just pay attention to something. I will be, when I'm talking about the curl, it will be this operator. It will be derivative with respect to coordinates x in the x hat plus y in the y hat, z in the z hat. Of course, you can just consider it in spherical, cylindrical, or whatever coordinates. It's derivatives with respect to the coordinates of R. Then I will also use this one with a prime. This will be x hat del over del x prime plus y hat del over del y prime plus z hat del over del z prime. This del prime will be derivatives with respect to the primed coordinates. So I know B, the first line over there. Let's take the curl of it. You see, B depends only on R. It doesn't depend on R prime because I'm integrating over the R prime coordinate, so the integral cannot depend on R prime. B depends only on R. I can only take the curl of B with respect to the R coordinate. So the curl of B. This will be equal to mu 0 over 4 pi integral over my volume curl of J prime cross R minus R prime over R minus R prime cube. Again, this is just one notation to simplify it a bit. When I say J prime, it is J at the point R prime. I just don't want to write R prime all the time. Now we have this vector identity. Or let's just calculate what this curl of the product of two vector fields. Now this B is not the magnetic induction, it's just an arbitrary vector field. This is another arbitrary vector field. So that's what I would like to calculate. If it was just A cross B cross C, this would have been B A dot C minus C A dot B. Well, A is now the curl, the del operator. Well, it is basically the same. You see, keep in mind, here I'm taking the curl with respect to the coordinates of R. This only depends on R prime, doesn't depend on R. So I don't need to worry about the derivatives of this thing. J of R prime cross R minus R prime over the same thing, magnitude cube. This will be equal to J of R prime times divergence of R minus R prime over R minus R prime cube minus J of R prime that the del operator acting on R minus R prime over R minus R prime cube. Well, this is taking the derivative of this factor. That is why in this expression I put the C over here. Because one of these A will be the derivative operator, it's taking the derivatives of C. In this case, it's this del operator which is taking the derivatives of this one. Why not? Well, you see here I am taking the divergence of this one, multiplying it with this vector. Here I'm taking the scalar product of the derivative operator with J acting on this one. Now let's forget about the magnetic fields. Let's remember our electrostatics. The electric field of a point charge was up to a constant R minus R prime over R minus R prime cube. The divergence of the electric field is proportional to the charge density. Well, for a point charge, the charge density is just a Dirac delta. So this is a Dirac delta function over here. That divergence, if you just go back in your notes, this is nothing but 4 pi times the three-dimensional Dirac delta of R minus R prime. So now we have, let me take this one. This is equal to mu 0 over 4 pi dv prime j of r prime times 4 pi Dirac delta of r minus r prime. This is my first term. Minus mu 0 over 4 pi dv prime j of r prime scalar product with this del operator acting on r minus r prime over r minus r prime cube. Well, the first term is easy to evaluate, it's just a Dirac delta. Now that Dirac delta tells me that since I'm integrating over all possible values of r prime, To evaluate this integral, I just replace everywhere in the integrand, I replace r prime with r. So these 4 pi's will cancel. Well, in fact, this cancellation is basically why we define that constant in the expression of the Biot-Savart law as mu0 over 4 pi rather than just some constant mu0. So curl of B is equal to mu0 times j of r. Then I have the additional term. Now I will use one more trick in that derivative. You see there I have derivatives, or let's say the gradient, derivative with respect to xi, the coordinates of the vector r, of r minus r prime over r minus r prime cube. I can change this to a derivative with respect to xi prime, but with a minus sign. Now, why can I do that? Let's look at in a simple one. Here I have a function of many variables, so let's just, for simplicity, let's just look at a function of a single variable. Let's assume we have a function f that depends on the difference x and y, x minus y. And let us take the derivative of this function with respect to x, not to y. This is nothing but derivative of f with respect to x minus y times the derivative of x minus y with respect to x. I'm just using the chain rule. But this is nothing but f prime at x minus y multiplied by 1. Now, if I take the derivative of fx minus y with respect to y, I can do the same trick. It is its derivative with respect to x minus y times the derivative of x minus y with respect to y. But this is derivative of f at the point x minus y multiplied with minus 1. So you see that if you have a function of x minus y, taking the derivative with respect to x and taking the derivative with respect to y, they are basically the same thing. They give you the same expression, but the difference is a minus sign. So that is what I am actually using over here. This depends on xi minus xi prime only. So if I differentiate it with respect to xi, or if I differentiate it with respect to xi prime, doesn't really make any difference. The only difference is this overall minus sign. So now let's look at that term only, this term. So there I have an integral over my whole volume, j prime, that the gradient del operator r minus r prime over r minus r prime cube. Well, I just said that we can write it as minus the integral over the whole volume j prime dot, not the derivative with respect to the coordinates of r, but derivatives with respect to the coordinates of r prime, del prime of r minus r prime over r minus r prime cube. Well, this is equal to, I will be using the chain rule. This is equal to minus dv prime, the divergence of j prime this gradient of j prime dot r minus r prime. Now let me erase it. Let me write it explicitly. Indices will be getting a bit complicated. This is equal to minus dv prime ji prime del over del xi prime r minus r prime over r minus r prime cube. I just wrote the indices explicitly. This will be equal to minus dv prime del over del xi prime ji prime times r minus r prime over r minus r prime cube minus del ji prime over del xi prime r minus r prime over r minus r prime cube. Well, if you would just take the derivative of this product, you get two terms. One term is the derivative of this one, multiplying this one. That is the term I want. You get an additional term, which is the derivative of this one, multiplied with this one. That doesn't exist on the previous line, so I subtract it. But you see now this is, you are taking the x component of j prime with respect to, taking the derivative of x component of j prime with respect to x, taking the y component of j prime, taking its derivative with respect to y, and then you are taking the z component, taking its derivative with respect to z, and summing them up. That is nothing but the divergence of j. So this factor over there is actually the divergence of j prime. But we know that in magnetostatics, the divergence of the current is always zero. Just remember, charge conservation tells us that del rho by del t plus the divergence of j is equal to zero. This is charge conservation. This is true all the time as long as charge is conserved. Magnetostatic means nothing changes in time. So this term is zero in magnetostatics, and hence this term should also be zero in magnetostatics. And hence the divergence of j should be equal to zero. So the second term is basically zero. But look at the first term. It is the integral of a total derivative. Well, the integral of a total derivative, I can always convert it to a surface integral. This term is also zero. Let me write it in this form. Let me take this term. Oh, no. This is equal to minus dv prime del over del xi prime of ji prime r minus r prime over r minus r prime cube. Now let me take the j component of this last term. So minus dv prime del over del xi prime ji prime xj minus xj prime divided by r minus r prime cube. This is a vector. Well, I'm just summing over I, but still I have a vector over here. So what I obtain at the end is still a vector. So I can talk about the components of that vector. So I'm taking one of that components. Well, this is nothing but minus dv prime gradient with respect to the prime coordinates of divergence of j prime xj minus xj prime. For each j over here, this quantity is itself a vector. the I component of that vector, of this vector. I'm taking the I component of the vector. I'm taking its derivative with respect to xi prime and summing over I prime. That's nothing but the divergence. But the volume integral of a divergence is always equal to the surface integral. But I'm integrating over all of space. Hence, this surface that I'm integrating over is the surface of my volume, which is at infinity. But at infinity, there are no currents. So this is also 0. So which kind of completes our proof that the curl of B is equal to mu0 times J. This will be always true for the magnetic induction field.
At the beginning, J was a function of R, and then we changed it to a function of R prime.
Where?
Why? Here is a function of R prime now. Let's scroll up. Yes, here is J, which is a function of R.
Where? Here. Well, you see, J is a function of position. At which point you are calculating J. That's what I care about. That position you can denote by R prime or R or whatever you want. You see, this equation, the curl of B I evaluated at the point R. So B at every point has a value. I can take the derivatives of curl of B knowing its value at nearby points. I know that this curl of B at the point R is always equal to mu0 times the current density at that point. Now, at the beginning, when I wrote the Biot-Savart law, is here. What I know is current everywhere will create a magnetic field. They will contribute to the magnetic field at the point R. So I need to calculate the magnetic field at the point R. I need to add the contributions of the current at the points R prime to the total magnetic induction at the point R. So here I'm just summing over all the different points, the contributions of different points. And those other points that I'm summing over, I denote their position as R prime.
Hocam bu J total J mi yoksa enclosed olan?
Well, you see, this is the total B I'm talking about. The total B will be the integral over all space of J everywhere. And here I'm not, you see, the advantage of this form of the Ampere's law is that there is no enclosing, there is nothing enclosing this one. This is always true at every point. I mean, this is a local law. This equation has to be, when you evaluate the curl of B at a point, it has to be equal to mu0 times the current density at that point. Now let's do a simple application of this one. Let's go back to our result of the magnetic induction created by an infinite straight current carrying wire. Now, initially, I don't know about, let's assume that I don't know anything about neither the direction nor the magnitude of the magnetic induction. But I do know several things. I know that my system has rotational symmetry. Nothing changes if I rotate my system around this axis. So that basically tells me that if I use cylindrical coordinates, B, which it will be a function of, let's say, S, phi, and Z, S being x squared plus y squared under the square root. Well, if I rotate my system, the phi coordinate of my points will be changing, but nothing in my system should be changing. So this rotational symmetry around this infinite line tells me that B doesn't depend on phi. At least the magnitude cannot depend on phi. This is due to rotational symmetry. Around this axis. Now, furthermore, I know that if I translate everything in the z direction, this is my z direction, if I translate everything in the z direction, again, nothing changes. But the z coordinates of my points will be changing. So nothing should change. Even if the z coordinate changes, it tells me that this magnitude of B should be independent of z. So the magnitude of B can only depend on the distance from the wire. Well, I don't know whether it will depend on S or not, but in principle it can depend on that distance. Now let's look at consider the direction of B. Again, nothing should change if I rotate my system. So that kind of leaves me with only two possibilities. Either B is in the radial, in the S direction, pointing away from my wire, but we know that B field cannot start from a point. Or there should be just rings around my wire. So since they cannot be just radially out from my wire, the only possibility is that it should be rings around my wire. So if it is just rings around my wire, so let me just consider such a ring. Let's say in this direction. So let me call that at this point, let me call this direction as my phi hat direction. So I know that B, the magnetic induction field itself, is Bs in the phi hat direction. Well, I don't know the direction of B. It can be either in this in the phi hat direction or in the opposite direction. So although I called Bs over here the magnitude, here I define my Bs as the component in the phi hat direction. It can be both positive and negative, because I don't really know whether it is in the phi hat direction or not. Now then I know that B dot dl should be equal to mu0 times I enclosed. This is my Ampere's law. Well, dl along that wire, well, just take one segment. This is my dl at that point. It's in the phi hat direction, and its length is also dl. Let's just call its length dl. So B dot dl is just Bs times dl around that loop, which this should be equal to mu0 times I enclosed. Well, let us call this radius the radius of my ring D. Here I'm calculating Bs on the loop, multiplying it by dl, and I'm doing this for all the segments, but for all the segments, S is just D. I'm just take this circle with center at the axis. So B of D times the integral of dl, since S is constant, this is just B of D, which is just a constant. I can take it out of the integral. So B of D times what remains is the integral of dl should be equal to mu0 times I enclosed. But this is nothing but the length of each one of these segments. If I'm summing all the lengths of all the segments, I get the circumference of my ring. And hence this is just B of D times 2 pi d. This is the left-hand side. Now let's look at the right-hand side. What is I enclosed? Okay, it is I, but plus or minus I.
Artı z yönünde olduğu için.
Who told you that the positive direction was in the plus z direction? How can you decide what is the positive direction of the current?
By right-hand rule, the magnetic field should be in minus phi there.
I don't know the right-hand rule for the magnetic field yet. I will drive it from here. How do I decide the positive direction of the current? Well, you see, whenever you are talking about magnetic fields, magnetic inductions, your right hand is your best friend. So again, it will be related with the right-hand rule. So just wrap your fingers in the direction of your loop. You see, my loop is going like this. So if I write my fingers in the direction of the loop, this is the direction of the positive current. My current is going in the opposite direction. So the current, enclosed current is minus I. So B of D is equal to minus mu 0 I over 2 pi D. Now this minus sign over here is what is telling me that the magnetic induction created by this wire is not circling the wire in this sense. It is circling the wire in the opposite sense. Now I know that I can use the right-hand rule to determine the direction of the magnetic induction. Take your right hand, your thumb in the direction of the current, your fingers curl in the direction of the magnetic induction. Now, the crucial thing over here about why we choose that direction to be the positive direction anyway is this identity. Let's say curl of any vector field integrated over some area. This is equal to the integral of G of that vector field over a closed loop, which is the boundary of that area. Now, the important thing is that you have to choose a direction for your area vectors, and you have to choose a direction for your dl vectors. And your choice has to be consistent with each other, in the sense that if this is your area, and if your area vector is pointing in this direction, this is your dA, then your thumb points in the direction of dA, then your fingers point in the direction of dl. In that case, this is our dl. You are free to choose this direction dA. You can choose this direction dA to be pointing on the opposite direction. But then dl will also be pointing in the opposite direction. So you have to be consistent in your choices of the direction of dA vector and also this dl vector. So that is why here, by choosing my loop to go in this sense, I have already made the consistent choice for the area vector, which is the positive direction of the current, is given by the right-hand rule. It is fixed. You are free to choose the direction of dl. Okay. Let me choose it and everything else will be exactly the same. It's just naming. if I had chosen my my loop to be pointing in the other sense, in that case, I wouldn't have obtained this minus sign. So B, this component of B in the other sense wouldn't have this minus sign, but that is still pointing in the same direction. So you are free to choose the direction of your loop. Well, of course, in this problem, we have the cylindrical symmetry. And if you are to use these conventional unit vectors, the S hat, the phi hat, and the Z hat, you would have chosen it the other way around. But you don't have to. You are free to choose it whichever way you like, as long as you are consistent with yourself. And your consistency enters into your calculation in this step.
Hocam şimdi DA vektörü DA'de hep her zaman dik.
No? Well, you see, the problem, okay, I would say no, but with this grain of salt. You see, DL vector is on the boundary. At every point inside this area, there is a dA vector which is pointing in a different direction. You see, if I take this sheet, this surface, and then I can choose at this point the dA vector can be pointing upward, and as I go over this surface, the dA vector will be pointing in different directions. I will be changing continuously. Now, when I reach the boundary, dA vector right at the boundary is perpendicular to this dL vector. Now, also this dL vector is constantly pointing at different directions. Here it's pointing like this, here it is pointing like this. But if I again just take the limit as I go to a boundary, this dA vector right at the boundary is perpendicular to the dL vector right at the boundary. But then, of course, you have other problems like how do you define the area on the boundary, etc. So rather avoid it. Any last questions before the break? So see you after 10 minutes.